That's right. So this is going to be the last of it. And then I'll put up my last module tonight. This is it. This is it for you,
Right.
I should say, this is it for Colinga.
Oh, yeah,
Harnell,
yeah.
you guys, you still got to deal with me for another 6 weeks. So
We should have a reveal party next Wednesday. Where the students reveal their faces.
uh, that would be cool. Yes, that would be
Yeah.
pretty. Okay. So yeah, next week is going to be so crazy for me. So we have the science forum, which is where my students in my 1A class in physics and math, they're all going to be presenting in front of an audience. So it'll be fun. So that'll be perfect for reveal. We use the last part, get to see you guys. And then I'm going to play some
But
of your,
what was that?
I said next week, there is a science forum at
Uh-huh.
Kalinga. Yeah. And so it's where
Oh, okay.
students, they present the work that they worked on, their projects.
Mm-hmm.
And so normally I would do this with your class as well, but your class is all online. So it's a lot harder to organize. So I haven't quite got that integrated yet. I'm going to try to figure
Yeah.
out.
Okay. For the when we do our presentations, through Zoom, we have
Yes.
to like okay, so like one person has to share the slides and then the rest of us, do we have like our what do you call it? Our cameras on? Or how does that
Yes.
work?
I would like to have your cameras on because I like to see your expression as you're answering questions. And then
Okay.
for the other reason is because, uh, as I said, I've learned a little bit along the way. I had a few people when I asked them a question, what they would do, they would have their phone there and they would actually use that to use the AI to sit there and question.
Okay.
So
I
yeah,
got
yes. Yeah, I'm like, if students would put as much effort into trying to cheat as they put into getting the work
into the
done,
class.
I know, man, they would just be brilliant, you know?
Yeah.
So
One time my son told me, he's like, Mom, are you even trying if you don't cheat? I was like, be quiet. But he's smart. He's like he's already like way ahead of me. But I was like a child. You need to
yeah.
chill. He's
Okay,
gonna
so
straight A's.
so you guys already know how to write chemical formulas. We've been doing it since the very beginning. You guys are like experts at it, right?
I think so.
For the most part, right?
Yeah.
So in this case, you know what the subscript means. You know what when you use your parentheses. Um, you're feeling pretty confident, right? So, like for instance, if we have the formula sodium nitrate, so we know that it's going to be sodium and nitrate together. So we have sodium, and then we have the nitrate polyatomic ion. We know that they have to be balanced out. We're good to go.
Right.
So if we looked at this, we know how many of each of the different elements that we have in this compound, right? So, like for instance, we know that we have one sodium. How
Three.
many? How many nitrogens?
Three? One. Oh wait, one, sorry.
One. That's right. And how many oxygens?
Three. Three.
Okay. So we know from our periodic table that our sodium, we'll pull up our periodic table. Sorry, I probably have 50 things open. I apologize in advance. There you go. So we know that the sodium is going to be 22.99. For simplicity, we're just going to round it up to 23. We know that the nitrogen is going to be 14.007. So for simplicity, we're just going to round it up to 14. it up, round it. And then we know that the oxygen is 15.999. So we're going to say, oops, okay. We know that we have three of them, so we're going to multiply that oxygen by 3. We're going to multiply our nitrogen by 2. And then we know we only have 1 sodium, so we're just going to keep it as it is. We add those together, so that's 28. And then that is 48. So then we can add it all together. Slide this over. Okay, so then for the entire compound, that sodium nitrate,
About 99.
okay, so it's, you said 99.
Yeah.
And the units are going to be, if we're talking about at a particular level, we'll talk about 1 molecule or something like that, 1 molecule of it, we'd call it 99 AMU. Okay, if we're talking about a large level, we're going to be using grams per mole. Okay. Okay, so when we're working with it in the lab, we're weighing things out, we're going to use grams per mole. Any questions? Okay, good. Okay, so that's how we would determine what we call its atomic mass. Okay, so we're getting the mass of the whole molecule, or we could say it's molecular mass, the mass of our molecule. Okay. So here we have ammonium carbonate. So I'd like you guys to tell me how many atoms of each element are in the formula unit of ammonium carbonate. So the first thing that we have to do is figure out what is the chemical formula for ammonium carbonate. Okay, so we know ammonium. It reminds us of what chemical that we know?
Is that the NH3 or NH4?
NH4 with a positive charge.
Okay, so we know that it's NH4 with a positive charge.
And then carbonate is C, 3 oxygen with a -2 charge.
Okay, so and then carbonate is CO3 with the -2 charge.
And we're rounding it up to on this one too.
We will be rounding it up. So, but the first thing that we want to do, the first thing that we have to make sure is that we have the compound balanced.
Oh, okay.
Okay, so that's going to be our first step. So we know that we have a +1 charge, we have a -2 charge. So we want it to add up to be neutral. So it has to add up to 0 altogether. So then how many ammoniums am I going to need to be with my carbonate?
Well, we're gonna need 2.
That's right. We're going to need 2. Okay, so then my chemical formula is going to be NH4, parentheses,
Two.
right, 2. Now, we use our parentheses when we're talking about, let's say, particularly in this case, polyatomic ions, when we have multiples of polyatomic ions. So the time that you use your parentheses is when you have multiples of something, okay? And it has to be something that's bonded together, okay? Okay, so that would be our chemical formula. So if we go through and calculate, we're going to calculate or break it down in terms of the number of atoms, and then afterwards we're going to calculate its atomic mass or its molecular mass, okay? So how many nitrogens do we have?
2.
Okay, so we have 2 nitrogens. How many hydrogens?
8.
How many carbon?
1.
And how many oxygens?
3.
3.
Okay, so that would be the breakdown, right? Okay, so then we know from our periodic table, everybody has a periodic table available. What's going to be that mass on the nitrogen?
14.
14. And we're going to be multiplying it by 2 since we have 2 of them. What about our hydrogen?
1.
1, and we're going to be multiplying that one by 8 since we have 8 of them. Carbon?
12.
12. And we're going to multiply that one by 1. And oxygen?
16.
16 times 3.
Calculator.
That'd be 96.
Is it 96?
Yeah.
There's something going on with Zoom. It keeps closing down and coming back up. So we add it together. And you said 96, right?
Oh, I forgot the other 48.
No, sorry, that isn't 48. It should be 24. My brain isn't working.
Oh, okay.
I mean, not 24. 28, not 48. There we go. 28. There we go. So then that's what? 1, 2, 3, 8 times 3. So that's 16, 24, 6. Plus. So 2. So that's 2, 4. That's 96, right?
Yeah.
Okay. Okay, so then it's going to be, if we're talking about, again, if it's a small amount, it's going to be use AMU, atomic mass unit. So that if we're talking about 1 molecule of it, or if we're talking about 2 molecules, we're going to use AMU. If we're talking about planning to use a lot of it, we're going to be using grams per mole. Grams. That's 4. So those are your choices. Okay, so I'll give you an example in a second. Okay, so when we talk about molecular formula is just going to represent the average mass of molecules of a compound. And the way that we want to kind of look at it is that is molecular formula is when we're mainly talking about covalently bonded items, where formula mass is going to be when we're talking about ionically bonded items. Because when we talk about covalently bonded items, they're one unit acting together. Covalently bonded items, when we're talking about covalently bonded items, it's one unit acting together. When we're talking about ionic bonded items, they're going to be interacting by electrostatic forces. So they're going to be a couple of them interacting together. The way that we do it is exactly the same way, but we're just making distinctions between the two. So let me show you what I mean. So this here is carbon dioxide. It's all one compound together. It's not together by electrostatic forces. There's bonds between them. They're covalently bonded together. So when we add it together, we have this is one carbon dioxide molecule. So it's oxygen is 16, and then carbon is 12. So we end up getting 44.0 units when we add it together. Okay, similar to what we did before, because we know that this is carbon dioxide, CO2. Now, your book prefers to use U, but U is going to be the equivalent as AMU, or you can use MU for mass units. You'll see them written in different textbooks and even in this books as well. Now, when we talk about formula mass is ionic compounds that are interacting together. So literally, we have, it's going to be, okay, you got to excuse my crude drawings. So the blue is going to represent, I'm going to make it looking like this. So that's going to be our ammonia or our ammonium. And then the pink is going to represent the nitrite. So it's 1, 2, 3. Okay. Okay. So these guys are really going to be alternating with each other, but because they're alternating with each other, we're taking the average mass of them. So then, in other words, you know that for every 1 ammonium you have 1 nitrate. Okay. So it's going to be a 1-to-1 ratio of it. So then when we calculate its formula mass, all we're doing is we're just taking a look at it. We're going to write down the formula like we did before. So what is the chemical formula for ammonium?
With ammonium nitrate
NH4.
or
And then,
NH4.
with a positive charge.
no.
Okay. And then nitrate, what is the chemical formula for nitrate?
NO3 with 1 negative charge.
Okay. Okay, so now they're going to balance each other out perfectly, 1 to 1. And so when we're calculating its mass, we're just saying we're only looking at that one unit. Okay, so that one formula unit. So in that case, it's NH4, NO3. And that would be the unit. Okay, so then in this case, how many nitrogens do we have?
2.
And nitrogen weighs
14.
15 times 2.
28.
Trying to keep me from making the same mistake twice.
Oh, I forgot. It's because my math teachers before would just say the question and then like we have to respond with the answer.
Okay. No, that's all right. Okay, so next, how many hydrogens?
Or
And it weighs
1.
okay, 1 times 4, we know is 4. Okay, and oxygens.
16. Oh, there's 3 oxygens, but they weigh 16.
Okay, there's 3 oxygens. I'm like, where are you going to see the 16 from?
The weight.
Okay, 16 times 3.
That's because I'm writing it down as well.
Uh, okay, so we're going to add them together. Let's see, 16 plus 4, so that's 20. So 80.
Yep.
And then we could say units, AMU, or just MU. It all means exactly the same. And then if we're talking about large quantities, we're going to be using grams per mole. Okay, so those are going to be your units for those. Okay, so we know how to calculate the molecular mass or the formula mass. They're all done the same way. So we also talked about the mole. So we know that the mole represents quantity, right? So 1 mole of substance is going to be 6.022 times 10 to the 23rd. You can drop that last 2. I prefer having it. I don't know why. It's because that's bad on the mole. So we also know that this is Avogadro's number. It's also called Avogadro's constant. Anytime that you hear that, you know that that's what you're working with. Now, since we know the mole, right? And we know that the mole is based upon carbon 12. So we can actually use this to sit there and determine how many molecules or how many atoms, how many stepchildren we have, because we know that the mole is just going to represent the quantity. Okay? Does that make sense?
Yeah.
Okay. And so we don't want to mistake it for mass. So when they're asking us for mass, that's going to be different than when they're asking us for quantity or moles. Okay? If they ask you how many atoms you have, that's going to be quantity. If they ask you how much does it weigh, that's going to be mass. Okay.
That's good you clarified that because I was getting confused on that.
Yeah, a lot of people do. And the other thing that other people get mistakes on is moles and molecules. Moles, just it's a quantity. It's like a dozen, right? We have a
Yeah.
dozen donuts. We know that that's 12. So when we say we have 1 mole, we know that that's 6.022 times 10 to the 23rd, or whatever you're talking.
Right.
Okay. So a sample contains 0.25 moles of ammonia. How many ammonia molecules is this? Well, we're going to start off with our given. And now we know that they're talking about quantity, right? How many? So we know that ammonia is NH3. And we know the conversion. How do I convert from moles to quantity? What am I going to use?
You need to use Avogadro, but the number
Number.
6.022 times 10 to the 23rd.
That's right. So we're going to put our 6.022 times 10 to the 23rd on top. Okay, and then that's going to be molecules. Because that's what we want, is the quantity of molecules of ammonia. And we're going to put 1 mole on the bottom, because that's what we're trying to get rid of. Okay, so then ammonia, moles of ammonia are going to cancel out. And then we're just left with our molecules. That 0.5. $1.505, I believe. 0.055, if I remember correctly. Times 10 to the 23rd molecules. Now, how many sig figs do we have? Or should we have? How many do we have here?
3.
You sure?
Oh, 2.
2.
That's right. So we have 2 sig figs here, right? Because we know that that 0 isn't going to be a significant fig. So at the end, our answer should be 1.5 times 10 to the 23rd molecules. Okay. Okay. Questions?
No.
Okay, so we've already talked about how to do the molar mass. We know that concept, we know what it is. So now we're just making it reference to it in that regard, right? So let me clear. And so when we're talking about molar mass, we're always going to be using grams per mole. So then that allows us to go from mass to quantity, okay? So I'll say that again. That will allow us to go from mass to quantity, okay? Calculate the molar mass of calcium fluoride. First thing I need to do is to do what?
The formula?
I need the formula. That is correct. Okay, so what is the formula for calcium fluoride?
CAF.
Yeah.
Okay, Ca, calcium. And are you sure it's CAF? Do you want to put money on that?
Probably not.
Okay.
Fluoride, isn't it just F?
Yes, fluoride is just F. What is the charge? What is gonna be the charge?
Oh, the charge. It's
Mm.
-1 or 1 minus.
That's right. And what is gonna be the charge on our calcium?
It's gonna be 2 plus.
Positive 2.
That's right. So then how many?
Extra fluoride.
When you need another fluoride.
Mhm.
Okay, so then I'll need one more fluoride. So then my chemical formula is going to be Ca.
So let's start out with this absolutely stunning
Okay.
graphic that we've got. This is from Mercedes 47 studio camera. The sunset
Okay. Now, again, I'll point out because a lot of students make this mistake.
is some gorgeous.
The charges are only when they're in their ionic form. So when they're ions, that's when it's charged, right? So when it's a compound, there's no charge associated with it.
This Saturday, this was
Or when they're metals, there's no charge associated with it.
and then the full
Okay. Okay, so let's calculate the molar mass of calcium fluoride. So how many calciums do we have?
1.
We did keep the
One calcium.
60 for the high, 67 on Monday. After that,
Calcium weighs
closer to average.
19 rounded up.
Mid-70s, and then today.
Are you
40.
sure?
I think it's 40.
40.
Oh, calcium. 40.
General.
Fluoride.
Okay. Fluoride weighs, we said 19 rounded up, right?
Yeah.
Okay, so we have 19 times 2.
President Stanford agrees by sale in Madeira, so this almost does a good job of this.
38.
Okay. So that's
That's
38.
78.
As much as what we've been seeing for the last couple days, we're only talking a few degrees. Here's the last 12 hours radar satellite. We do have a few thin high clouds around right now.
So we're going to add those together.
That's something that we've had around off and on throughout.
So we get 78.
These clouds stick around for the
And the
next-
units are going to be, because they asked for a molar mass, and then it kind of tells you the units. Molar, moles.
So it's the grams per mole or just moles?
That's right. It's grams per mole because it's molar mass. So we're going to be putting grams per mole.
Okay.
In the valley,
I was just putting the bottom.
the skies,
Okay.
closer to the crest of the Sierra
You beat me to it. Okay. So we'll fix that.
Or high elevation snow shower. Tonight, we're at 54 for your low, we'll be tomorrow afternoon. In Fireball 54 tonight, we'll have 83 degrees on the way. Heading into Fresno County, if you're in Mendota.
Okay.
Please. Present 15.
But you always remember when they ask you for molar mass, right? It's moles and mass. So your units are going to be your grams per mole.
46 today, low, 76 for the high, 52 tonight, 74 tomorrow. Three Rivers, we do have an 80-degree day in the forecast tomorrow.
Okay.
Send the forecast.
So if we take a look at these items, right? Each of these represent 1 mole
Sunday
of substance.
morning
right?
trend. See down to 76,
So
closer to average.
1 mole of nitrogen, well, that's going to be 28 grams per mole, right? That's what's in that balloon. We have 55.85 grams of this. So that's 1 mole of iron. We have 26.98 grams per mole of aluminum. So then this represents 1 mole of aluminum. Now you'll look at it and you'll recognize that these are not all going to be the same because they're different. Quantity wise, right? They all represent 1 mole, which we know is 6.022 times 10 to the 23rd. So this is what 6.022 times 10 to the 23rd of iron is going to look like, that quantity. So if we counted each of the atoms of iron, 6.022 times the 23rd, but it weighs 1 mole of that is going to weigh 55.98. Okay, so it's that helping us understand quantity versus mass. Okay, and so that's the same thing when we talk about compounds. So this is copper 2 sulfate pentahydrate. Well, here's that chemical formula. That's how much it weighs for 1 mole. This is what 1 mole looks like. Okay. Does that make sense? So like
A little bit.
we can't visually see a single molecule of copper sulfate pentahydrate, but we can play with a mole of it, right? which is 6.022 times 10 to the 23rd. We can clearly see that. We can see a mole of it, but it's hard for us to see and visualize one molecule of it. Okay, so you're carrying out a reaction. Let's say you're carrying out a laboratory reaction that requires 0.0360 moles of barium chloride. How many grams of the compound do we measure out? So here we're going to be using its molar mass. Okay, so what is the chemical formula for barium chloride?
So we need 1 barium and 2 chlorides.
Okay, so we're going to have 1 barium and 2 chlorides. Okay, so 1 barium, 2 chlorides. So we know barium weighs
137.
Remember, it's 137.22.
3,
Oh,
3.
we're not rounding it.
33. Yeah, here we want to be careful with rounding because it always
All right.
it can bite you in the butt. If it's like really, really, really close to a whole number, then you can round. Like oxygen, really, really close to a whole number. But here we know that this is chlorine. Chlorine is what?
35.45.
45.
35.45, right? So here we will want to round because they're like right in the middle. It's pretty close, and that's going to have an impact. So we're multiplying that times 2. So that's going to be what? 70.9. And then, of course, this is going to be times 1. So it's just going to be its number, 137.33. So we add those two together.
To help protect your family. That's why
208.
23.
0.23.
And you have a choice of options.
And that's grams per mole.
Nope.
$2 a week, 35 cents.
Okay, so now we have this, right? So that's going to represent our molar mass. We're going to use our molar mass to figure out how many grams that we actually have because we're going to be starting off with moles. So our starting off point is our moles. So we have 0.036 moles
I filled in all my important information in the final list.
of barium chloride. Okay, now we want to get rid of those moles and we want mass. So we want to put the moles on the bottom. So we know that per mole means 1 mole.
6515775.
And we're going to have 208 on the top. So we're going to be multiplying it by that mass.
Obligation 1-800-651-5775. Call now.
Okay, and that's a barium chloride.
Cost was estimated at more than $1 million tonight.
Okay, moles of barium chloride are going to cancel out. Then we're going to be left with grams of barium chloride.
Vintage Days is returning to Fresno State this weekend.
The 3-day event kicks off this Friday on campus. You can enjoy live performances, games, crafts, events.
Is this where we need whole numbers?
What was that?
Do we need whole numbers on this part right here?
No, we don't need whole numbers. We can
No?
have, we can have decimal numbers.
Okay.
Experience. There will also be a drone light show on Saturday night near the Resnick Student Union to mark the event's 50th anniversary.
Capital, which one of the flights has been.
Okay, how many sig figs do we have?
That is the delay.
Is there floor?
Nope.
Some stunning clouds next couple of days.
So remember these these zeros here in the front, they're not going to count towards significant figures.
Oh, so 3?
So we have three. So we're going to take a look at the 6. Is 6 greater than 5?
Yes.
So we're going to round it up. Our answer is going to be 7.50
After tea to
grams of barium chloride.
and value veterans back home after spending 3 days visiting war memorials. I look at the suite for Union and the left.
CBS Don't Miss Survivor and the Amazing Race. Followed by Andy and Pearl. Winning from Unified 5 Jump Chancey Gold Resort and Casino.
Get ready to make a splash this summer.
It's the $600,000 target the pontoon boat and jet ski.
Okay, so when we're converting from quantity or units, right, to moles, we use Avogadro's number, right? That Na, that's what that represents, Avogadro's number. When we're converting from moles to grams, we're going to use the molar mass. Okay, so again, when we're going from units to moles, we're going to use Avogadro's number. When we're going from from moles to mass, we're going to use the molar mass. And same thing applies the other direction. Okay, so the way that we distinguish this, when we look at things, when we measure things like macroscopic quantities, so that's going to be working with things in mass and mole. So we're going to be using that molar mass. Okay, when we're talking about the particulate,
We
Right.
have experience.
the individual atoms and stuff like that, that's going to be going from moles
People's
to
lives
quantity.
transform and change for the better.
That's what we literally
Okay. Now, what do I mean? Determine the mass in grams of 3.2 times 10 to the 24th molecules of sulfur tetrafluoride. We want to get the mass, but we're starting off with molecules. What are we going to do first?
The energy that creates, because this is a woman.
The chemical formula?
We want the chemical formula. Okay, so we have sulfur tetrafluoride. What is the chemical formula?
1 sulfur and 4 fluoride.
Okay, so we have 1 sulfur and 4 fluoride. And we want to make sure to use subscripts because this is a compound, right? So that's the way we'd write the chemical formula. So then we know that we have 3.2 times 10 to the 23rd molecules of this. So we can go 3.2 times 10 to the 24 molecules. So if I want to get the number of moles, how would I do that? If I have molecules. What am I going to use?
It's the avocado.
Avocado number
Yeah.
Avogadro's number. That's right.
6.022 by 10 to the 23rd.
Okay. And so that's going to be molecules.
The top is mole. That's grams.
And that's going to be moles on top. That's right.
Yeah, mole.
Okay. But we want to get to mass because we want grams, right?
You want grams.
So, yeah. So what am I going to do that? So how can I go from moles to grams?
Yeah. 1,000? No.
1,000?
No. I was like, no. I'm thinking milligrams.
So we want to go from moles to grams. What do you guys think we're going to use?
The molar mass.
The molar mass. So we're going to have to calculate the molar mass. So we know sulfur tetrafluoride, you already told me it has one sulfur. Sulfur weighs
32.0 or 30.
32.0. So I could say we can round that one,
Yeah.
right? 32.
Yeah.
Okay. And fluoride weighs
18.998.
so we can round that up to 19 times 4. And we're going to add those together.
108.
So that's moles or grams per mole.
Grams per mole. Okay. So then we can use that
Over here.
to get rid of our moles. So we put the 1 mole on the bottom per mole, and then 108 grams on top. Okay, so then molecules cancel out, moles cancel out, and we're left with just grams. What did you guys get? Okay, so how many sig figs should we have?
Was it 2?
2. Okay, so my answer is 570, and that should be grams of SF4. Okay, any questions? No questions?
Oh yeah, I
No.
got a question. Sorry.
No, that's right.
What calculations did you have to do to get that 573.8?
Okay, so we have 3.2 times 10 to the 23rd. So if I'm entering it in my calculator on my computer, I entered 3.2, and then I go EE. There's an EE button, or you'll see EXP, same type of situation. And then I just type in 24.
Okay, okay.
And then I'm going to divide it by 6.022. And then I put EE 23. And then I'm going to multiply that by 108. Now, if I wanted to, I could also just put the 3.2 times 10 to the 24th times 108, and then just divide it by that.
Okay, okay. All right. That makes sense. Thank you.
You're welcome. Okay, let me clear. Okay, so when we talk about percent composition of mass, it's going to be the part over the total. Okay, so when we talk about a chemical compound, we're talking about, we may be looking at just the fluoride and calcium fluoride. Okay, I mean, so in that case, or the fluorine and calcium fluoride. So we know that earlier we wrote calcium fluoride was CaF2. And when we talk about the compound, that's the whole thing. But if we're talking about the fluoride in the compound, that's going to be the part over the total. Okay, so we know that calcium, if I remember correctly, it was 40 plus 38, because we know that the fluoride was 19 times 2.
Yeah, that's right.
That total is going to be 78, right? And so we said grams per mole. Okay, now the fluoride is 38. So if we're going to do the part, we're going to put 38 over 78. And of course, grams per mole. So the grams per mole is going to cancel each other out. So then, and then we're going to multiply it by 100. Then that's going to give us our percent mass of fluorine. So we'll just put F. Okay. So what we get.
Yeah, 0.487179.
Now, don't forget to multiply it by 100.
Oh yeah, I forgot.
We're looking at the
Yes.
percentage, right?
Oh man.
So taking the numbers you gave me, right? And because we're using the numbers from the periodic table, we're not going to have to worry about significant figures here, right? Unless they tell us specifically what they want. So we could use 3 sig figs, or we could use 2 sig figs, whatever floats your boat.
Okay.
So now, since we know that this is going to be the calcium, we can sit there and, this is going to be the fluorine, how much fluorine we have in our compound. So we can figure out the amount of calcium by either subtracting that 48 from 100, because 100%.
This is now the comfort of a flip
So
flop.
that's going to be
So often. So it feels like a flip flop.
51.3%.
But now, so maybe you're going on the air.
Calcium.
I am not.
Okay. Or we could sit there and do the same thing with the calcium. We could have put 40 per mole
Now we're getting that super light
over the 78
everyone loves.
grams per mole
And I want to say these laces are elasticized.
times
So
100.
going to give you, the adjustability.
And if we done it right, we should end up with the exact same number, right?
Favorite feature is the inside is actually with tearing.
51.
So it feels like the super softest little
Okay.
wrap your baby in, and it's going to get away moisture. Then you're getting 13 millimeters of cushioning. That is a huge deal, because in most comfort shoes you have 4 to 5 millimeters, but we are giving you 13 millimeters. Last call down, last call right. You more than that.
Okay, so let's keep going. Are you guys good? Ready for the next part?
Yes.
Yeah.
Okay. So calculate the percent composition by mass of aluminum sulfate. First thing I need to do is to do what?
Chemical formula.
Chemical formula. Okay. So what is the chemical formula for aluminum?
Yeah.
Okay. And then chemical formula for sulfate?
Is it SO
And then. Out.
SO4
So 4 with a -2 charge.
minus? Yeah.
Okay. So what is the charge on aluminum?
3.
3 plus. Okay, so I told you if these guys are not divisible by each other, we can do that cross multiply.
So
Oh,
2
yeah.
aluminum and 3 sulfate.
That's right.
Even gets another presentation after this, it'd be 2 colors. And.
Okay, so we end up with Al2
Ourselves a little bit. That's right, but there's always next year.
SO4, and that's going to be in parentheses. 3. Okay, so that's going to be our chemical formula. So if we're going to calculate its atomic mass or its molar mass,
Then we have the steam.
how many aluminum do we have?
We have 2
Two.
aluminum.
Okay, so we have 2 aluminum. Aluminum weighs
26.982.
26.9882.
Yeah, 82.
So we can say 27. Close enough to it. Times 2. I correct my math because I'm working on 1 brain cell. How many sulfurs do we have?
3.
I have 3. Okay, we know sulfur was,
32.06.
so we can say 32 times 3.
But the energy return buoyancy,
And then oxygens,
which is buoyant.
12.
Right, because we can make a super soft shoe, but then.
and oxygen weighs
16.
It's almost like that's.
16.
That's too soft, wait till the next day.
So I can't do this one in my head, so I'm gonna
192.
192. Thank you.
Mhm.
Did you do that from your head?
No, I have a calculator.
Oh,
I am not like that. And it's 342.
Here's one where I say, getting whole and half sizes and.
and that's grams per mole.
Yeah.
Okay. So now if we want to look at each of the different elements, start with aluminum first, since it starts with an A. So we want the percent mass of aluminum. So I'm going to put percent mass. Okay. So we know that that's going to be equal to
Then we have it in the pH.
mass of the aluminum
Next is
Four.
denim, and it would surprise me a lot with the fact.
divided by 342
Started to show we had
times
and that with that
100.
with our warm beige,
okay,
black woven. And then we love the idea. of why we don't do that.
15.8.
We have it in
15.8.
Oh yeah, 15.8.
Is that what you said?
Yeah.
Okay, so then for the sulfur, we have 96 over 342.
Times 100.
Cloud steppers. Cloud steppers are all about really lovely, cushioning, softness. We made them so you would love every step. And the drift outsole in particular was based on.
That is 28.1%.
What we did is we kind of added these rows to the outsole.
And then we have oxygen. So we can do it 2 ways. The easiest way is to just take 100
So like you have an inch and 3/4 of the back.
minus 15.8 minus 28.1.
Two straps in the butt. You have a square out, which I think is actually that we're seeing a lot of brown toes, but the square out, but we've seen a lot of brown toes, but the square actually just got a pair of other.
56.1.
What did you get?
Oh, 56.1%.
Okay. Okay, that's it. Okay, how's it going so far? How's your head going? Good?
Good.
Okay, good. We're gonna keep going for a couple more minutes and then we're gonna take a break. Okay, so aluminum chlorate is 38.35% chloride. What mass of aluminum chlorate is needed as a source of 50.0 milligrams of chloride? Okay, so if we think about the definitions, right? We have, to put it simply, we have the part over the whole, and we multiply it by 100. Then that's going to give us our percent mass, okay, of the part. Okay, so this is asking us, it says aluminum chlorate is 38.35% chloride. So we have our percent of the chloride, right? So we can kind of plug that into this equation here. 38.35%. Okay. And it says what mass of aluminum chlorate is needed. So how much aluminum chlorate is needed if we're going to get 50.0 milligrams of chloride? So we're given the part, so that's going to be 50.0 milligrams. And we're trying to figure out how much of the whole we have. So this is unknown. So we're going to put an X here, not an X. Let's use a Z since we use times there. Okay, so we're multiplying times 100. Okay, so then what we're going to do is solve for Z. We want to get Z all by itself. Okay, so to do that, what am I going to do? Well, simple thing is to multiply both sides by Z. Okay, so then this Z cancels out, and then we're left with 38.35 Z. Okay, and then that's going to be equal to 50.0 times 100, which is 500. Okay. Okay, so then to get our answer for Z, we're going to divide both sides by 38 now. Okay, so then this is going to cancel out, and so we're going to get Z is going to be equal to, how did you do that?
130.4.
130.4.
Yeah.
And so that would be milligrams. Of the aluminum borate. Okay. And so if we're doing 3 sig figs, right? Well, this has 3 sig figs, so we need to end up with 3 sig figs. So it should
So it'd just be 130?
yeah, it'll be 130. But
Okay.
we'd have to write it in scientific notation.
Oh, okay. 1.30 times 10 to the 2.
Okay. Questions?
So with these kinds of questions, the answer always has to be in scientific notation unless like stated otherwise, or
So you can get away. It doesn't have to be in scientific notation, but by writing in scientific notation, you can write 3 significant figures. If you just put 130, that's only 2 significant figures. Right?
oh,
So
to
if you become-
0. Yeah.
become zero.
Okay, okay. Yeah.
Unless we put a decimal there, then that would make it 3 significant.
Okay.
But it always looks pretty.
All right.
Okay. So we've used that percent mass, right? And so this is just kind of helping us remember that whole concept and how to go through that process. So we're going to keep going. Okay, so when we talk about empirical formulas is going to be the formula so that we have the lowest integral ratio between the 2 atoms or the atoms that are in the compound. So for instance, if I have C4H10, so that basically means that I want to try to find the number that I can get this so that it has the lowest integral ratio. Right? So I can divide both of these by 2, and then that's going to give me C2H5. C2H5. So if I have C6H12O6, what would be the empirical formula for that?
Would it be C3H6O3
Okay, are you sure?
We can go by
divided by 2 divided by 6?
So if I divide everything by
Yeah, so it'd be CH 6,
H6 and then O.
CH2
huh?
and then right? Because you're
Oh,
dividing
yeah,
everything.
yeah.
Okay. Okay. So what if I have
Inside it's leather. No, it's leather. And then we have this beautiful block here.
N2O9?
N4O3.
Okay. So that's the empirical formula. Now, the reason why the empirical formula is going to be important is that when you're working in chemistry, some of the instrumentation will actually determine the empirical formula. It'll let you know how much of the nitrogen that you have relative to your oxygen, or how much carbon you have relative to your hydrogen that you have relative to your oxygen. And so the instrumentation will give you the empirical formula. And from that, you have to try to figure out what the molecular formula is, right? And so that's often what happens. So there's like programs, algorithms that will allow you to sit there and do that calculations and figure out what are the possible different compounds that could be with that empirical formula. And it also will do, depending on the instrument that you're using, the instrument could also help identify not only the ratio, but approximately how much you have of that. And so then that can be used to figure out the molecular form. Okay. So the way that you're going to calculate your empirical formula is often going to be based upon moles and mass. Okay. So here we're given a sample of a pure compound that is made up of 1.61 grams of phosphorus and 2.98 grams of fluorine. Find the empirical formula for this compound. So we know that it's a compound, it's bonded together. We need to figure out what is the chemical formula for that empirical formula. Okay. So the way that we go about doing that, do you want to help me out, Juanita?
Okay, hold on, let me read it. I just came back because my daughter needed her bag. A sample of a pure compound is made up of 1.61 grams of phosphorus and 2.98 grams of fluorine. Find the empirical formula of the compound. Do we have to put the grams
Okay.
by the
So we know that we have 1.1 grams of phosphorus.
Mhm.
And then we have 2.98 grams of fluorine. So what would be the next step? Because we want quantity, right? Because that ratio is quantity. It's not mass. It's quantity that we see when we talk about, carbon dioxide is 1 carbon to 2 oxygen. That's quantity, right? So what are we going to use to get to quantity?
We have to use the 6.022 times 10 to the 23rd.
No, that gets us there, but there's also another thing that we can do. Since we have mass, right? We're starting off with mass.
Faster.
What's going to get us to quantity, starting with mass? Because we know that moles is also quantities, right?
So we
So
have to
what are we going to use?
moles?
We're going to use what?
I don't
So
know.
we have grams. We're starting off with grams.
Milligrams? No.
Oh, no, that's specific. You're getting too specific.
I'm so obsessed with milligrams.
Yeah, we're starting off with grams. We want to get to moles, right? We want to get to that quantity. So if I'm going to go from grams to moles, what is it that I need to figure out?
Grams per mole.
I need to get my grams per mole. So we know that phosphorus weighs how much?
30.974.
So 31 grams per 1 mole of phosphorus. Okay, so then grams of phosphorus is going to cancel out, and then that's going to give me my number of moles. So
I'm gonna put it right here with you. I'm gonna put it right here with you.
can you hold on 1 second? I think I heard somebody at the door. Hold on 1 second. But you guys can do the calculation. Figure out the next one.
$49.9.
What'd you get?
Whoa.
I got 49.9. That would be mole for phosphorus.
I got something else because it's
Yeah, I got something different too.
I
I
got
probably
0.
messed up.
I got 0.6 or about 0.05.
Oops, I multiplied.
Oh,
It
I'm
happens.
tired today.
yeah. It's
Yeah.
okay.
Yeah, it was a hot day today, bro.
0.05
0,
and
5.
366, so it's 0.059.
Yeah, like that.
Yeah,
Moles of phosphorus.
And that's moles.
And then for the fluorine, how much does fluorine weigh?
Where is it?
I see a price, I feels like I just don't.
Oh,
18.998.
19 here.
Sunny over 26 years. Remember, because it is 6 and it was 20 and I was pregnant in October of the 20.
How much numbers are right there?
All right.
Okay, so what did you guys get?
.157.
Okay. So then what we're going to do is we're going to take the one that has the lowest number and we're going to divide it, both of the numbers by that. Okay. So in this case, the one that has the lowest number is the phosphorus. So we're going to divide phosphorus by itself. And we're also going to divide this one by itself. I mean, not by itself, by phosphorus. Okay, so when we get that, we know that this is going to give us just one. So that means that we have one phosphorus. And then this one lets us know how many fluorines we have per phosphorus. So this guy gives me a value of 3.025, blah, 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 right? But we need whole numbers since we know that when we write our chemical formulas, they're whole numbers. So
Oh,
it's
this is where we need the whole numbers.
that's right.
Okay.
So we're going to need approximately 3, right? Because it's really, really close to 3. Okay, now since it's so close to 3, then we're just going to round it to 3. Okay, if the number, let's say it ended with 3.2, right? Then in this case, we need to figure out a way of getting it so it would be a whole number. So what could I multiply 0.2 by?
By 5.
Okay, so I can multiply 0.2 by 5, and that would give me a whole number. Okay, so I'd like to give a little table to everyone. Let's see. Point 5 is going to be multiplied by 5. 0.333. Oops, I forgot one. 0.25 is going to be multiplied by 4. 0.333. That's going to be multiplied by 3. 0.5 is going to be multiplied by 2. 0.667 is going to be multiplied by 3.
4.
0.75 is going to be multiplied by 4. And then, wait, is that right? Yeah. And then 0.8. I mean, 0.8 is going to be multiplied by 5.
Fine.
Okay. So anytime that you get numbers after you divided it by these and one of your numbers ended with this, then that means that you're going to multiply both of these numbers by whatever number you get, right? So let's assume, let's say we ended up with, one, in this case, nitrogen, and we ended up with 1.667 oxygens. Okay, so then what we would do in that case, since it ends with 0.66, we're going to multiply it by what?
3.
We're going to multiply it by 3. So you multiply that by 3. And then you're also going to multiply this by 3. So this is going to give you 3 nitrogens. And then this is going to give us, what is it?
Let me see. 5? It's like
Okay.
5.00.
And I can't even. Three nitrogens, 3 N's, and then this would be 5 oxygens. So my empirical formula would be N3O5. Okay. Okay, it says nicotine is 74.1% carbon, 8.64% hydrogen, and 17.3% nitrogen. What is the empirical formula? So what are we going to do here, right? Because this percentage represents percent mass. So what is an assumption that we can make?
Like take the percent out, maybe?
Okay, so we can take the percent out. So basically we can say that we have 70.1, or we can make the assumption that we have 100 grams of our compound. So if we have 100 grams of our compound, that means 70.1%, 70.1 grams of it is carbon, right?
Mm-hmm.
Okay, so 74.1%. My brain is not working today. Grams of carbon. 8.64 grams of hydrogen, and 17.3 grams of nitrogen. Okay, so what are we going to do now that we have grams?
Change it to moles?
Change it to moles. Okay, so carbon weighs.
Is it 16 or 14 or 12? 12.
12.
Yeah.
Okay. Okay, so then we have 8.64 grams of hydrogen. So hydrogen weighs how many grams?
1.
1. So we have 1 gram per mole of hydrogen. And then nitrogen weighs
15 grams.
14 grams per mole.
That's 1.24.
Okay, so we're going to take the smaller number.
You divide everything by 1.24?
That's
Oh.
right. Because we're getting it relative to that one, right?
Yeah. So that would be like 5, because it's
Okay.
4.9.
Okay. So it's going to be approximately 5.
That one is 6.9, so like 7.
7.
And then 1. Nitrogen, 7 hydrogen, 5
Okay,
carbon.
so we have C5, H7,
And
N. Okay. Okay, so when we're determining the molecular formula, we're going to have to be given the molar mass of the compound, and we're going to have to calculate the molar mass of the empirical formula. So the first thing that we always typically have to do is find the empirical formula. But if we're given the empirical formula and we're given the molar mass of the compound, we can sit there and calculate the empirical formula, the molar mass of the empirical formula. Okay. And then you're going to divide the molar mass of the molecular formula or the compound, but divided by the empirical formula. So let me show you what I mean. So here, a compound with an empirical formula of C2H5 has a molar mass of 58.12 grams per mole. So this is the empirical formula. We're trying to find the actual formula of the compound. So we have how many carbons in C2H5?
2.
2. And we know that carbon weighs
12,
times 2,
24.
24. Okay, and then hydrogen, we have how many hydrogens?
5,
Hydrogen weighs,
1.
and we multiply that times 5. So we add that together, we get 29 grams per mole. Okay, so then we take this number, the mass of our compound, the molar mass of our compound. So that's 58.2 grams per mole. And we're going to divide that by 29. So if we do that, it's going to give us, again, here we want a whole number. If I remember correctly, that should be about 2. So then that means we take our chemical formula and we're going to be multiplying it by 2. So we're going to go C2H5, and then we're going to be multiplying it by 2. That whole thing. So then we end up with C4H10. Okay. Questions? Cash? Okay, let's move forward. Okay, so when we look at a chemical equation, right? A chemical equation is going to tell us about what's happening, right? So we have our reactants. Reactants are what we're putting into our reaction. And then they do what they do, and then we get our products. Okay, so you guys remember these are the reactants on the left-hand side of the equations. And then these are our products. Reactants. Now, the reason that we have to have a balanced chemical equation is so that we can sit there and figure out how much of stuff we're going to need if we're trying to make so much stuff, right? So, in other words, we know that these numbers here are going to represent quantity. So we get to figure out quantitatively how much do we need if we're going to be producing this much stuff, okay? So let me give you an example. How many of you guys bake cakes?
Sometimes.
Sometimes, okay? So do you bake it from the box or do you bake it from scratch?
Oh, from the box.
From
I
the
like
box.
to cook. I'm not a baker.
Okay,
Yeah.
okay, okay. That's fair because occasionally I will make cakes from scratch, but it's usually special occasions. But most times that I make cakes, it'll be from a box.
From a box.
Yeah. So when you're making that cake from a box, there's that general recipe. Roughly, you have your box of your
Mhm.
cake mix, right? Plus, typically it's about 3 eggs. Me, I like butter, so I put butter in there rather than the margarine. So it's about a stick and a half of
Uh-huh.
butter. And then I think it's 2 cups of water. Really, I think it's like 1.5 cups, but yeah.
Yeah.
I usually use milk
Oh, yeah. Uh-huh.
because I like mine, dairy rich. Okay. And that's going to make 1 cake. Now, let's make an assumption that our 1 cake will feed 8 people.
Okay.
And let's say I'm going to have a party, right? And I'm having 64 people coming over.
Okay.
Yeah, I like to throw big parties.
All right.
Okay. So, how many cakes am I going to need, first off? And
8.
then how many eggs and how many cake box mixes and am I going to need? Okay. Okay. So, how many cakes am I going to need to feed my peeps?
8. 8 times 8. Yeah.
That's right. So, I'm going to need 8 cakes. So, I need 8 cakes to feed all my people. Okay. So, if I need 8 cakes, I can start off with 8 cakes because it's a quantity, right?
Uh-huh.
And then I can use this balanced chemical equation to calculate how much I need of each of the things. So 8 cakes. So the ratio between cakes and boxes is a 1-to-1 ratio. So I'll need 1 cake then I'm going to need 1 box of cake mix. Okay, so then that's just going to be 8, right? So I need 8 boxes of cake mixes. Eggs. So if I start out with 8 cakes, I know the ratio is a 1-to-3 ratio. So for every 1 cake, which is going to be on the bottom, I'm going to need 3 eggs. And so that's going to be 24
24.
eggs. Okay. And so I could do the same thing for butter, and I could do the same thing for water, right? So using the chemical equation, and all the chemical equation is just a recipe, right?
Yeah.
Using that, we can figure out how much our products we can make, and we can also figure out how much of our reactants that we're going to need. And so that's what we're going to be doing with stoichiometry. So this process is called stoichiometric ratios, right? So basically, we're looking at the ratio based upon the chemical equation, okay? So here, this chemical reaction says that if I have 4 ammonia, I'm going to need 5 oxygen to make 4 nitrogen monoxide and 6 water. Okay, so that means that for every 5 oxygens, I'm going to need 4 ammonia. Or I could say for every 4 ammonia, I'm going to need 5 oxygens. So we're going to use that ratio, right? And we're going to use it, and we can flip it so that we can sit there and do the calculations for one thing or the other, okay? And so that's similar to here with the oxygen and the nitrogen monoxide, okay? So for every 5 moles of oxygen, I'm going to need 4 moles of nitrogen monoxide, okay? And here, for every 5 moles of oxygen, I'm going to need 6 moles of water. So we need to have a balanced chemical equation so that we can figure out what we're going to end up with at the end, okay? So we always have to have a balanced chemical equation, which everybody learned the first week of class or second week of class. Okay, so let's write down that chemical equation. Okay. Oh, no.
4?
That's 4.
Yeah.
I had to get it eventually. What was how many ammonia?
It's 4.
It's 4 ammonia. So then it'll be 4 here. So make sure it works. 4. So that's 12, 4, 4. That doesn't quite work. It has to be 6.
It's 6, yeah.
Water. How'd it got there? Eventually, 6 waters.
I got confused because you said ammonia.
Oh,
And I was looking at the nitrogen monoxide.
uh,
So I still wasn't even.
okay. So now, since we have our nice balanced chemical equation, it says if we have 3.2 moles of ammonia, so if 3.2 moles of ammonia react according to the equation, how many moles of water will be produced? So here's our equation. So we want to calculate the water. So our starting point or our given is going to be our ammonia. So we're going to go 3.20 moles
In each three.
of NH3. Okay.
Mhm.
Actually, I'm going to use the abbreviation. Okay.
Mhm.
And so since we have moles of ammonia on top, we want to get rid of ammonia on the bottom. So by putting it on the bottom. So we have 4 moles of NH3. Now we want water. So that's what we're looking for. So we want to get water. Okay. So in this case, we're going to be putting
1
6 moles
6.
of water. Right. So again, we're going to be using the ratio that we have
Okay.
in our balanced chemical equation. And then that's going to give us our moles of water. So what is that?
4.8.
Said 4.8?
Yeah.
You're quick with that calculator.
Oh yeah, it's like if I were doing math mentally.
So that's it, right? And so everything that you've learned up until this point is, again, it's dimensional analysis, and it's thinking about what you know, right? You're going to use that ratio from that chemical equation. So that's the biggest thing that we need to remember. You need a balanced chemical equation. You need a balanced chemical equation so you can use the ratio to sit there and calculate how much of your product or how much of your other reactants you're going to need.
Okay.
Okay.
Mhm.
Did the guys go or are they still here?
I don't know.
Let's see.
They're still here.
Good. Hey, we got one more than we had.
Really? Oh, there were 5 before, huh?
There were, well, 5 including me. So,
Oh,
okay.
Julian joined.
Yep. Okay, so we're going to convert. When you're converting from moles of reactants to moles of products, we know we need to use that ratio. That's all this is telling us, right? So whenever we're going from the quantity of the reactant to the quantity of our product, we're going to be using moles. Okay, it's always going to be that pattern, the mole-mole ratio. Okay, so how many moles of oxygen are required to burn 2.40 moles of ethane? Well, what type of reaction is this? If it's a burning reaction,
Is it combustion?
it's
No.
a combustion reaction. That's right. So we know in a combustion reaction, we have C, they're telling us we're burning ethane. So it's C2H6, and that's a gas. And it's going to be reacting with what if it's burning?
Oxygen.
Oxygen. What is the chemical formula for oxygen?
O2, isn't it?
That's right. O2, because it's a diatomic compound. And we're going to be making, what are the products in the combustion reaction?
What was that? Does it combine? No.
No,
That's
combustion.
that's combination. Yeah.
What do we blow out?
Carbon.
Carbon what?
Oh, carbon monoxide, huh?
Not
No,
carbon
carbon dioxide.
dioxide. That's right. And water. So it's always going to be carbon dioxide and water. Okay. So is that balanced?
No.
What do I need to do to balance it?
Hold on. Let me write it out. CO2 plus H2. The carbons, there's 2 and 1. Hydrogen to 6 and 2, and oxygens is 2 and 1. So you can multiply a 2
Okay,
for
two
carbon.
and what? What's on it over here? How many oxygens?
Oh, there's 3.
Okay, so we need to multiply our carbon dioxide by 2.
Uh-huh.
Okay, so then that gives me 2 carbons, and that's a total of 5.
Oh,
5 oxygens. Okay. And then,
um, the 6 and the 2 you can multiply by 3.
okay,
And then that gives us 6.
and then that gives us
7.
Mhm.
But oh yeah, okay, I see it.
okay. So what do I need to do now? Since since
I
this is an odd number and this is
I
an
know.
even number,
Like, why does it have to be an odd number?
remember, just take that odd
But-
number, put it on top.
And then the 2 on the bottom.
Okay. So then we have to multiply the whole thing by
The whole thing by 2, right?
that's right. Okay.
Then it would be like C4. You have to do the whole thing, right?
Yeah. So we'll go through and rewrite it.
H12.
So 2, 8.
But
No,
we only multiply the subscripts, not the
we only-
coefficients.
no, we multiply the coefficient.
Oh, the coefficients, not the subscripts. Okay.
We put a 2 in front of there. So plus 7, I mean 2 times 7 halves. So that should just be 7. Okay, so we're at
Oxygen.
oxygen.
Then
Okay. Okay, so now we have a balanced chemical equation. We may want to check it just to be sure. So what we have 4 carbons. 4 carbons. We have 12 hydrogens. 12 hydrogens. We have, let's see, 14 oxygens. So that's 4 times 2 is 8 plus 6. That's 14. Okay.
oh, okay.
Okay.
Yeah.
Okay. So we are at now we have a nice balanced chemical equation. We're going to use our given. So a given is going to be 2.40 moles of ethane. Okay, and we want to calculate the number of moles of oxygen. So what am I going to do now?
We have to cancel out the moles.
Okay, you're right. We're going to cancel out the moles. So I need to look at the number of moles of my ethane. Okay, so my chemical equation says I need 2, right?
So
So I'm going to put my 2 down here, 2 moles of ethane.
2H6.
Okay, then what's going to go on top? What do we want?
Oxygen?
Oxygen. So we look up here. We have how many moles of oxygen there?
7.
7 moles of oxygen. Okay, so then those are going to cancel out, and we transfer it over to the amount of oxygen that we'll need. So then that is 1.2 times 7.
Is it 8.4?
Three significant figures, 8.40 moles of oxygen. Okay?
Okay.
Okay, good. Okay, so when we go, we're trying to get from mass to mass of, let's say, mass of our reactant to the mass of our product or something along those lines. Then what we're going to do is we're going to follow this kind of guideline, this algorithm. We're going to take the mass of our given. That's our starting point. We're then going to get the moles of our given, and we get that by using the molar mass of the given. Then we were going to get the moles of what we want. So then we're going to use the molar mass, the mole to mole ratio from the chemical equation. Then we're going to use the molar mass of the wanted, what we want. Okay. And then that's going to give us our mass of what. Okay. So this is just saying exactly what I just said in the last slide. And this is just helping us know that we could sit there and use this process, this step from any process. So if we're given mass, we're going to be using the molar mass to get the number of moles of our reactant. Then we can get the moles of our product by using the mole to mole ratio. And then we can get the mass of our product by using its molar mass. Okay. And then we can also start off with the quantity, so we can use the quantity, number of molecules, to give me the number of moles. And then that moles can give me the quantity in moles, and then I can get the quantity as number of particles. Okay, so moles is our gateway drug. Okay, so I'll say that again. Moles is our gateway drug. Okay, here we go. Now, how many milligrams of nickel 2 chloride are in a solution if 503 milligrams of silver chloride is precipitated in a reaction of silver nitrate and nickel 2 chloride solutions? Okay. The first thing that we need to do is to do what?
Chemical formula?
The chemical formula, or in this case, it's going to be a couple of chemical formulas. It's going to be the chemical equation, right? So let's go ahead and figure out what is our chemical equation. So it says that,
Nickel.
let's see, it says nickel 2 chloride. So that's going to be one of the things that we're working with, are in a solution if, say, how many nickel 2 chlorides solution if silver chloride is precipitated. Okay, so silver chloride is going to be precipitated. So the chemical formula for silver chloride is what?
Silver chloride, you said? Ag.
CL.
That's right, AgCl.
Thank you.
Okay, and that's the chemical formula. And it's a precipitant, so it's going to be a solid. Okay, and that's going to be one of the products. So that's going to be on the right-hand side of the arrow. So what's going to be on the left-hand side are the two things. It says in a reaction of silver nitrate So silver nitrate, chemical formula for silver nitrate.
Be AgNO3 1 minus.
That's
Yeah.
right. But we know that silver is going to be 1 plus, because silver is always 1 plus,
Uh-huh.
unless they tell us otherwise. So silver is always 1 plus. So we won't, these are going to balance each other out perfectly.
Yeah.
So we're going to need
Oh, okay.
nitrate. So remember, there's no charge on it if it's right. And it's a solution. So that's anytime it's a solution, it's going to be aqueous. AQ. Okay. Plus nickel 2 chloride. So if we have nickel 2, what is the charge on my nickel? Symbol for nickel is Ni. So what would be the charge on my nickel if it's nickel 2 chloride?
2.
Plus.
It'll be 2 plus, yeah. So then how many chlorines am I going to need to balance it out?
2.
So I'm going to need 2. I'm going to need 2 L minuses. Okay, so then my chemical formula is going to be NiCl2. And then that's going to be aqueous, AQ. Okay, so what type of reaction is this going to be? We got 5 choices.
Let me look at this. Ag. And,
Double displacement.
It's going to be a double displacement. So we're going to be switching partners, right? So we know that the Ag is going to go with the Cl. Okay, so that's what we have already. And then the nickel is going to go with the nitrate. So if it's nickel 2, how many nitrates am I going to need?
2.
I'm going to need 2. That's right. Because we know that the nitrate is a -1 charge, and we'll need 2 of them to balance it out. And anything with nitrate is going to be aqueous. It's going to remain aqueous. Okay. Okay. Is it balanced?
No.
No. So we need to balance it next. How many silver do we need?
Isn't it just 1?
Okay, so Ag right now we have 1 and 1. Nickel, we have 1 and 1. Chlorine, we have 2 and 1. And then nitrate,
1
we
and
have
2.
1 and 2. That's right. Okay, so how can I balance out my chlorines?
Multiply by 2.
Okay, so we're going to put a 2 in front of here. So that means now we have 2 silver and we have 2 chlorines. Chlorines are looking good. Okay. So how can I balance out my silver now?
2.
Put a 2 in front of here.
Yep.
I'm going to slide it over so you guys can see it. Okay, so 2. And so then that gives me 2 silver. And that also gives me 2 nitrate. So we're good now, right? Good and balanced. Yeah? Okay.
Yes.
Okay, good. So I'm going to have to erase this to make room for our next part. Okay. So I'm going to show you guys the long way to do it. So our given is what?
503 milligrams of silver chloride.
503 milligrams
Mm-hmm.
of silver chloride. Okay, So we have milligrams, but when we calculate our molar mass, that's in what units? Isn't it grams per mole?
Oh, yeah.
Yep. So then how would I get from milligrams to grams?
The divide by 1,000 or 100?
That's right. We're going to divide it by 1,000. And so we're going to keep that unit of our given. And that's going to be 1 gram of AgCl. Okay. So that gives me my grams of AgCl because these guys are going to cancel out those units. And so we're just left with the grams of AgCl. So if I want to get to moles, how am I going to get to moles?
Is that with the 6 point?
No,
Not that
'cause
one.
that would give me quantity. That would give me
Oh, yeah.
moles.
Quantity. Oh, yeah, it's so confusing for me. Molar mass?
The molar mass. So how many silver do we have in silver chloride?
Oh, 1 and 1.
1 and 1. Okay. So, and silver weighs how much?
107.87, so 108.
Okay. Yeah, we could almost get away with that. So we're going to say 108.
Mhm.
And then it's 35.45.
Yeah.
Right. So let's, since it's 107.8, right? If it's 9, we're going to round up. So we're going to go ahead. So it's 107.82.
Okay.
Is it 82 or 887?
It's 87.
87. Okay, so we're going to go ahead and add those together. So that's what? 1.
Let me see. 7.
So 143.
Yeah, 143.32.
Okay, so then we're going to use that, and that's grams per mole. Okay, so 143.32 grams on the bottom, 1 mole on top. And that's of AgCl.
Mhm.
Okay, so then we've gotten rid of grams, and now we have moles. Okay, so if I have moles of AgCl and I want moles of nickel 2 chloride, so what am I going to do now?
You have to do the molar mass for the other ones?
We're going to have to do the molar mass, right? Or not the molar mass yet. We're ahead of the game. One more thing.
Oh, wait, what was the question again?
If I want to get from moles of silver chloride to moles of of nickel 2 chloride, what am I going to use?
What do you use? You're pointing at it and I still can't get it. The grams?
No, because we're in moles now. What is this? What do these numbers represent? Are they mass or are they quantity?
Those are quantity.
Those are quantity, right? So moles is quantity, right? So now we just need that mole to mole ratio. So for every 2 moles,
Oh, okay.
there are 2 moles of silver chloride. So 2 moles
Mm.
of AgCl. 1 mole of nickel 2 chloride. Okay.
Okay.
So then next we have moles of nickel 2 chloride. So what do you think we need to get to grams?
Is that when we use the molar mass?
That's
of
right.
that?
We're going to need the molar mass of nickel. So we know that nickel weighs, or how much nickel do we have in our nickel 2 chloride?
Maybe just 1? Yeah.
And then Cl, we have 2. So then
Nickel
yeah,
is 58.
35.45 times 2. And then nickel weighs how much?
58.693.
Okay. So, and we're going to add those together. So that's 3. So that would be
129.83.
okay. So you said 125. You
No,
said
129.
129.83.
0.83. Mhm.
Are you sure?
No, that's wrong. I didn't put the 6
Okay.
in the 693. Hold
Okay.
on. 58.6. 3. Wait, what did I tell you before? Is I got 129.593. 58.693. That's multiplied by 1, right? So it's like the same. Yeah, 58 point plus 35 point. Oh, yeah. Yeah, it's 129.593.
There we go. Okay. So then we're going to use that 129.593. And that's grams for 1 mole. And that's of nickel 2 chloride. Okay, moles of nickel 2 chloride are going to cancel out. And we're going to be left with, oh, we're not done yet. Because we got to go to milligrams, right? Because they want milligrams.
Yeah.
Yeah. Okay, so let's go ahead and add our milligrams. We know that for every 1 gram, we have 1,000 milligrams.
Yes. Open MG, open MG. Yes.
Okay, so let's see if we can get rid of anything to make our lives a little bit easier. Okay, so that's going to cancel out grams. So 1,000 milligrams are going to cancel out here, and 1,000 is going to cancel out here. So then we're going to be left with our units is going to be milligrams. So I'm going to end up with milligrams. So this is going to equal. And then, so we don't have to worry about the thousands because they cancel out. So we have 503 times 129.593 divided by 143.32. And then we're going to divide it all by 2. Here's my calculator.
Yeah, let's see if we got the same thing because I included the 1,000. So
It'll
that's
end up being the same because you're multiplying and you're dividing. So
okay. Oh yeah, because it'll cancel out anyways, huh?
yeah.
227.411. How many sig figs? 3. So 227.
So we have 3 sig figs, so it'll be 2, 2, 7, and then there's 4 following it, so 227.
Yeah.
There we go.
Oh, it was a long way.
Yeah, it's a long one.
This is like the one that's in the
Your homework. Yep.
in the homework. Yeah.
And then also the one that we had on the, oh, you didn't have it on the practice.
On the what?
It'll be on your practice test for your final.
Oh, on the practice test. Oh.
Good and clear? Did
Okay.
everybody get it? Everybody's good?
Yeah.
Okay. Okay, percent yield. Okay, so I'll tell you guys a quick story, and then we have to do the. So when I was in college, I took a class called Q Chem or not Q, analytical chemistry, AChem. So I took analytical chemistry, and analytical chemistry is basically it's learning how to use instrumentation and then calculating your percent yields and your percent error and things like that. Okay. So, and I'm a first generation college student. None of my family members ever went to college, and I'm not good. I was never really good in the beginning of sharing stuff and asking people about stuff and everything like that. So I made assumptions about them, and sometimes my assumptions were wrong. So I had in second quarter. So this would be my fourth quarter, because we were on the quarter system. I took analytical chemistry, and I did really good in general chem, and so I was like, I'm going to kick analytical chemistry's butt. So I go in there a little bit cocky and everything like that. I got my lab mate and everything, and my lab mate was privileged, we'll say. So he actually drove. I can't even think of what he drove. It's a really, really fancy car. Wasn't a Benz. It was it's the one that has the like the Cougar on the front, or the
Oh, yeah, Jaguar.
Jaguar. Thank you. He drove a Jag, and he got it for his graduation gift
Wow.
for high school, and so pretty privileged. But he was not like the sharpest knife in the drawer, if you know what I mean. He was like, box of rocks. So that was my lab partner. His name was Jacob. Now, me and Jacob, we'd go through, and I would prep the labs. Like, I would go through before I did any lab. I'd write down all of the procedures and everything like that, because I like to check things off. Because otherwise I forget. And I like getting my lab done fast, quick and fast and right. So checking it off, I always made sure I did it right. So I was going through it, and I did the lab, and this was our very first lab, and we were looking at percent yield. And so I went through, we did a calculation, and I'm sitting there thinking, okay, so we're going to get 100%, right? Because 100% to me means an A, and if we're doing it right, we should get 100%. So we did the experiment and everything like that, and I did my calculations, and I got 82.3%. And I'm like, that does not seem right. So we had finished before everybody else. We had time. We did it again. Right? And then, I said, we get the same results, 82.3%. So we did it a third time, 82.3%. And so Jacob was like, I think we're good. I think we're good. He's like, it's got to be good, right? So we asked this other kid, again, another privileged kid, and his name was Aaron. And Aaron said that he got 100%. And I'm thinking, I'm smarter than Aaron. Jacob may not be smarter than Aaron, but I'm smarter than Aaron. There's no way that he got 100% and we got 82.3%. There is no way, right? So I made Jacob stay one more time, and we did it, right? And then we got 82.3% again. So I was upset. I was really upset. And then, again, being a first generation college student, I'm sitting there thinking, fucked up. This is what I think is my wheelhouse. I should be able to do this. I must have made a mistake. I know I made a mistake. So I went and grabbed some food. I told the TA, I was like, hey, is it okay if I come to your afternoon lab? Because he had two labs. He had one, I think it was at 2 to 5 was ours. And then he had one after from 6 to 9. So I asked him if I could come to a 6 to 9. And he said, yeah, sure. Ken, yeah, come on. And he's like, what? He says, you guys didn't finish? I'm like, no. I said, we finished, but we didn't get the right answer, right? And he just kind of looked at me kind of weird about it. And he's like, yeah, he says, you can come back. So then I tried to talk Jacob into coming back, but Jacob didn't. So I'm like, that's all right. I said, I can do it myself. And I said, I'll give it to you if I get it right. So I go back and I do the lab again. 82.4%. Did it one more time. 82.1%. Did it one more time, 82.3%. I am pissed, right? I am so mad. I'm like, and at that point, although I do have a little bit of a temper, but my temper at that point was a lot worse. I was so mad. I took my lab notebook and I tossed it in the garbage because I'm thinking to myself, you know, here, this is what I want to do with my life. This is what I feel I'm good at, and I can't get it. And that guy who isn't as smart as me, right, got 100%. How in the hell did he get 100%? I've checked everything. I've done everything I'm supposed to do, right? And then so I'm mad and everything like that. So I pack up everything and I put it away and I'm cussing as I'm going out and I slam the door. And the TA kind of looks and watches me do this and he's just kind of looking at me. And then as I walk out the door and I start walking down, he decides to take a step out. And it's funny because at that time I was sitting there thinking, I'm done. I'm just going to drop out of college because obviously I'm not meant for this. And he yells at me. He said, Mr. Henry, what the hell is going on? What's wrong with you? Right? He's like, you throw your lab notebook, and he took the lab notebook out of the garbage can and he hands it to me. He's like, why are you throwing your lab book away? I told him, I said, well, I did this experiment. And I said, I've done it. I said, at this point, I've done it 7 times. And I said, I keep getting around, 82.3% roughly. And he's like, and I said, plus or minus or, point, 1 or, and everything. I said, but that's what I keep getting. And he laughs, right? And so then that makes me more mad. And I want to hit him at that point. I didn't hit him, but I was thinking about it. I was so mad. I'm like, why are you laughing at me? Right. And I literally said, why are you laughing? I said, it's not funny. I said, I always thought I was going to be good at chemistry. And then he keeps laughing. He's like, come with me. And so he takes me back into the chemical stock room. And he's like, okay, so if you've done this experiment, right, and everything worked out the way it's supposed to, right, what percentage did you think you should get? And I said, I should get 100%. And he kind of laughs. He's like, okay, so first off, chemistry does not work that way. He says, I want you to do me a favor. He says, look at this bottle. He says, this is the chemical you started out with. And the way that you guys did that experiment, this is the chemical that you should have ended up with, right? And he's like, so what is that percentage on there? So I look at the bottle and it said 82.3%.
Yeah.
And so the moral of the story is there's a couple.
Yeah.
One of the major things is that, you're going to fuck up. Things are not going to work sometimes, or you're going to think they didn't work where they
Right.
actually. So don't decide to sit there and bet your whole life on one experiment, right? Or 2
Right.
experiments, right? You're going to mess up. It's okay to mess up. That's part of learning. And so don't quit because you're bad at it initially, because you learn to get better, right? And you get better and you start understanding things. Right? So that's one thing. The other thing, well, don't cuss out the TA. That's another thing.
Oh no.
They're typically there to help you.
Yeah.
And then the other thing is that in chemistry, you're always going to have a low yield. You're never going to get exactly what you want because a lot of the times we're working with chemicals that are not pure. They already have contaminants in them, so their percentages are typically lower. Or sometimes it's just something that we do, right? That you're going to end up with a bad yield, or you can end up with a side product, okay? And then that's going to give you an even lower yield, okay? So don't give up at the end. So I told you my story. Let me show you how to do this. And then I think we may have enough time for one more. I'm going to do it real quickie. So the percent yield, so that is going to be the actual over ideal. And it's going to be multiplied by 100. So your ideal is what you're calculating with our calculations. Your actual is what you actually get. So let me show you what I mean. So here, a solution containing 3.18 grams of barium chloride is added to a second solution containing excess sodium sulfate. Barium sulfate precipitates. So that's letting us know that the barium sulfate is our our product. Okay, so I'm going to go ahead and write out the chemical equation since we're crunched for time. So we have barium chloride plus sodium sulfate, which is Na2SO4. And then that's going to yield barium sulfate plus sodium chloride. So this is going to be aqueous. This is going to be, since it's a precipitant, it's going to be a solid. This one is going to be aqueous since it's a solution. And then this one is going to be aqueous. Okay, so then we need to balance it out. So we're going to need 2 in front of here. And now we're balanced. Okay, so now we have a balanced chemical equation. So the way that we go about calculating this is we're going to use 3.18 grams as our starting point of BaCl2. So now, since we have grams, we need to get to moles of barium chloride. So we know that barium is 137.33. That's our Ba. And we know Cl is 35.45. And we know that there's 2 of them. Times 2.
137.33.
Yeah, what is it? 137.33. Yeah, 137.33 plus. So that's 208.
8.23.
So it's 208.23.
Grams.
And that's the grams per 1 mole. Thank you.
Okay.
And that's a barium chloride. Now what we want is our barium sulfate. So we go to our chemical equation. So this is going to give us moles of barium chloride. These are going to cancel out those units. So we want barium sulfates for every 1 mole of barium sulfate. We have 1 mole. Oops, sorry. Barium chloride at the bottom. This is what happens when you're trying to rush. Over 1 mole of barium sulfate. Okay, so then we're going to need, so then that's going to give us our moles of barium sulfate, but we need the mass of barium sulfate. So we know barium again.
137.33.
137. Wait, 3. We know sulfur is
32.06. Right?
say 32 to keep it simple. Then oxygen, there's 4 of them.
So 4 times 16.
Yep, times 4.
64.
4 plus 32 is 96 plus. So that's,
233.33.
you said 233.33?
Yeah.
Oops.
And that's grams.
And that's grams per mole. That's right.
Uh,
Okay, so we'll put 2, 3, 3 on top here. Whoops, 233.33,
Yes.
and that's grams, and that's 1 mole of barium sulfate. Okay, so moles are going to cancel out. And so ideally,
It's
we get
3.5 or 3.6.
3.56 because it's 3 sig figs, so 3.56, and that's moles or grams of barium sulfate. Okay, so this is our actual. This ideal is what we calculated. So if everything went perfectly, this is how much we should have ended up with. But this is what we actually ended up with. So in that case, we're going to put our actual divided by our ideal. And we're going to multiply it by 100.
And that's 94.6 or like 95%.
94.6%. 3 sig figs, so we're going to stick with 3 sig figs. Okay? And so that's how you would do percent yield.
Okay.
Okay. So you guys should look through the rest of the packet. More than likely what's going to happen is that, oops, because the next part is really good, this one here. But look through the next part of the packet, and then we've done most of it. So I will probably put in some extra credit questions, and they're going to be the stuff that we didn't go over in, we didn't get a chance to go over in the section for your guys's final for Kalinga. Now, Harnell, you guys, we'll go over the rest of it next week. So